Hello, and welcome to this video on the topic of magnetism. You probably already know that every magnet has two poles, north and south. Have a look at this magnet. If we suspend it from a piece of string which is attached to this point, then let go of it, what'll happen? The magnet will swing around so that its north pole is pointing northwards and its south pole is pointing southwards. For this reason, the poles of a magnet are sometimes called the north-seeking and south-seeking poles, but you'll be glad to hear that plain old north and south will be good enough for your exam. The poles of a magnet are the places where the magnetic forces which it can exert are strongest. When two magnets are brought close together, they'll exert a force on one another. Here, for example, these magnets will be attracted towards one another because unlike poles attract. If the magnet on the right is turned around, however, repulsive forces between the south poles of both magnets will try and push them further apart. The same thing would have happened had we pointed the north poles of both magnets towards one another. Like poles repel, you should spot that a magnetic force is an example of a non-contact force. Two magnets don't have to be touching for them to be attracted to or repelled by one another. A very smart question at this point would be, how does one magnet know that the other's there? In other words, how does it know whether to be attracted to or repelled by it? To answer this question, we have to learn a little about magnetic fields. A magnetic field is the region around a magnet where it will exert a force on another magnet or on an object which is made from a magnetic material such as iron, steel, cobalt or nickel. We can use a plotting compass to investigate the magnetic field around a bar magnet. A plotting compass is like a miniature version of one of the navigational compasses that people used to use to work out which way north was and where they were back in the good old days before we used our smartphones for everything. If we move a plotting compass around this magnet, the direction in which the north pole of its needle is pointing changes. Here, it shouldn't be a surprise to see that the needle is pointing away from the north pole of the magnet because like poles repel. But if we keep experimenting, we find that the needle maps out a nice big loop from the north pole round to the south pole like this. We've just traced out one of the magnetic field lines of the magnet. If we repeat this process, we can trace out a number of other magnetic field lines. As you can see, magnetic field lines always point from the north pole of a magnet to its south pole. The direction of the magnetic field at any point shows the direction of the force that would be exerted on a north pole in that point in the field. So here, the north pole of this compass needle points away from the north pole of the magnet and towards its south pole. We said that the poles of a magnet are where the magnetic forces which it can exert are strongest. Here, we can see that the magnetic field lines are closest together at the poles. The closer together the field lines, the stronger the field. You might also notice that the field lines get further apart with distance from the magnet, which means that the magnetic field is getting weaker. The Earth, of course, has its own magnetic field. This is what causes beautiful aurorae to be produced at the poles, or the northern and southern lights in layman's terms, and it also helps protect us from some of the potentially nasty cosmic radiation which we would otherwise receive from space. A compass needle will always point in the direction of the Earth's magnetic field, like this. Slightly confusingly, the Earth's north magnetic pole is actually in its southern hemisphere and vice versa. This is why the north pole of a compass needle points towards geographic north, because it's attracted to the Earth's south magnetic pole. On to the last bit of this video now. A permanent magnet produces its own magnetic field and will always have a north and south pole. If a magnet is permanent, then it can be both attracted to and repelled by another magnet. Let's use a diagram to explain what this means. Here, we're trying to find out whether or not this piece of metal is a permanent magnet. At the minute, we can see that it's being attracted to the magnet on the right. So far so good. But to test whether or not it's permanent, we need to see whether both objects can repel one another as well. If we flip the magnet on the right around, we see that both objects are now repelling one another, so yes, the mystery piece of metal must be a permanent magnet. Can you work out which end is north and which end is south? Unlike a permanent magnet, an induced magnet only becomes magnetic when it's placed into a magnetic field. If a magnet is induced, then it will only ever be attracted to a permanent magnet. Here, this iron nail is acting as an induced magnet. The magnetic particles that make it up are lining up in the magnetic field of the permanent magnet to the right. Like little compasses, which means that its south pole is located next to the bar magnet, like this, and its north pole is at the far end, like this. Because of this arrangement, the nail and magnet will be attracted to one another. If we flip the magnet around, the magnetic particles that make up the nail will flip around with it as they adjust to the new direction of its magnetic field. This reverses the poles of the nail, and so both objects will still be attracted to one another. An induced magnet will quickly lose some or all of its magnetism when the magnetic field that created it is removed. So here, if we pull away the bar magnet, the nail loses its magnetism. Let's finish off now with a quick example. Why not pause the video here and press play when you think you know the answers? In part A, the iron nail is acting as an induced magnet, which means that it will only ever be attracted to the bar magnet. In other words, its north pole is on the right and its south pole on the left, like this. For part B, you should remember that the iron nail will only be magnetic while the bar magnet is held close to it. When the magnet is pulled away, the nail loses its magnetism and the paper clips will fall. That brings us to the end of this video on magnetism. Think of it this way: if you're an induced magnet, then physics is the permanent magnet that you can only ever be attracted to. On that note, why don't you try the exam style questions before running out to buy yourself an old school compass? Good luck.